recording this session. Good morning and welcome to EE252 Electronic Devices and Circuits. Let's start the lecture from where we stopped last time. Last time we talked about feedback amplifier analysis, right? So in general, and we looked at how the, can you guys see the screen?
Yes, sir, we can.
Okay, thank you. So we looked at how each of the parameters change with feedback, right? You know, with negative feedback, how things change. We said that the gain always reduces by a factor which is known as D, right? D, the feedback amount is 1 plus beta A, where beta is the feedback gain, the gain of the feedback network, which is typically less than 1. A is the gain of the system without feedback, the original gain of the system, and this A can be, you know, a voltage gain, a current gain, trans impedance, or a transconductance, depending on whether you have a voltage amplifier, current amplifier, and so on, right? So we know that, and we said that the gain with feedback always reduces. This is basically equal to A divided by D. In other words, A divided by 1 plus beta A. Okay? This gain is reduced. Remember, D is greater than 1. Beta A typically is greater than 1. So therefore, in any case, D is 1 plus something. So it is not negative. So always D is greater than 1. So always the gain is reduced. Right? And the input impedance with feedback, depending on whether you have a series comparison or shunt comparison, it will either increase or decrease.
Excuse me, sir.
If the input is a voltage, in such case you have to subtract the feedback signal in series. So therefore, what happens is the input impedance increases, right?
Hello, excuse me, sir.
Yes.
Sir, your voice is not clear.
Okay. How about now? Oh, hold on. Let me change the source then. How about now? Is it better?
Yes, yes.
Okay. My voice is clear now. You guys can hear me now better?
Yes, sir. Yeah.
Okay, thank you very much. All right. Let me get back here. So, as I mentioned, D, which is the feedback factor, is equal to 1 plus beta A, which is a quantity greater than 1. And always, by introducing feedback, we are going to reduce the gain of the feedback, because we are going to divide the gain without feedback by D. So therefore the gain always reduces, but the input impedance, depending on whether it is connected in series, feedback is given in series, or shunt, will be changed accordingly. For example, this will be equal to Ri, the original feedback, times D. So that means we are increasing the gain, the input impedance, which is equal to Ri 1 plus beta A for series comparison. So that is when the input is a voltage, right? For voltage input or for series comparison. And this is when input is a voltage. Okay, so it increases and it will be equal to Ri divided by D, which is equal to Ri without feedback divided by 1 plus beta A for shunt comparison. When do we do shunt comparison? We subtract a current if the input is a current, right? So this is when input is a current, obviously. So these are desirable changes of the input impedance. For voltage inputs, we want the input impedance to be very high, so it increases the input impedance, whereas for current inputs we want the input impedance to be very low, so therefore feedback actually reduces it. So this is desirable. Okay, so similarly the output impedance are out with feedback, again depending on whether you have a voltage output or current output. In other words, depending on whether you sample it in shunt or in series, it will be either increased or decreased. So for example, the output impedance without feedback will be decreased, right? So this will be less than the output impedance without feedback for shunt comparison, right? Shunt, you connect another sampling network in parallel. You do this for voltage outputs, right? For shunt sampling, so this is done for when output is a voltage. Okay, and it will be multiplied by D for series sampling. In other words, we are connecting a sampling network in series, so the the output impedance increases. So this is when output is a current. Okay, all right. So these are the things that we looked at so far. Now today we are going to move on and analyze an example circuit. Right, we are going to look at an example circuit and do this analysis carefully and see how we can actually, what are the steps that we need to follow in order to analyze any feedback circuit. Okay, so this is an example along with how to do this. Okay, so this is, now I'm going to take a voltage series feedback circuit. Okay, analysis of voltage series feedback circuit. Okay, right, so I'm going to draw this circuit first. It's going to be like this. So you have, let me use a PNP transistor, right, to show that it is not much different from the NPN also in terms of analysis, right? Then I have an input source Vs. This is my source signal through a resistor. Let me call this Rs. This Rs may be the internal resistance of Vs, but in this case we are assuming Rs is not the internal resistance of the source, but it is part of the circuit itself, okay, but it can actually be the output impedance of the source also, but not in this case, right? And so this is the you connect it to the base, and you have the transistor. This is the emitter, so this is the base, collector, emitter, and the emitter is connected to an emitter resistor and grounded. Collector is connected to a collector resistor, and this is connected to a voltage source. Now because this is a PNP amplifier, PNP transistor, the current has to flow through in this direction. So therefore, since I am connecting the emitter to the ground, because remember this acts like a diode, right? So the current has to be flowing in that direction. So therefore, my VCC has to be negative. So therefore, let me mark it as negative VCC. So VCC is less than the ground potential. So this is my circuit that I am analyzing, and I am going to I'm going to take the output from here. Okay, so this is my output. This is my output. Remember, this will be the positive terminal. This is the negative terminal, because output I have I'm powering it with a negative terminal, negative VCC. So therefore, this is my output voltage, V out. So this is what I have. This is my circuit. Now tell me, is this circuit, what kind of a circuit is this? What kind of an amplifier is this? Is a voltage amplifier, current amplifier, transconductance amplifier, or a trans resistance amplifier? Can someone please tell me? Quickly. Hello? You guys can hear me? Hello? Can someone please respond?
Yes, sir, we can.
Right. So what kind of an amplifier is this? It's very easy to figure out. What is the input type? What is the output type? That's all you need to know. What is the input of this? Is it a voltage or a current?
Voltage.
It's a voltage. What is the output of this? It is clearly marked.
Voltage.
It's also a voltage. So what kind of a amplifier is this?
Voltage.
It's a voltage amplifier. Right, correct. So this is a voltage amplifier. We have a voltage amplifier. So we know what it is. So output is a voltage, input is a voltage. So what kind of sampling should I use? Series sampling or shunt sampling? Output should be sampled in series or shunt. Since it's a voltage, it's a shunt, right? You use kind of like a voltage voltmeter. So you connect it in shunt, in parallel, right? So this is a shunt feedback, shunt sampling, and because it's a voltage, you have to give the feedback in series or shunt.
Series.
In series. So therefore, what we have here is a series shunt feedback circuit, right? No, series shunt. Series shunt circuit. Okay. So we have figured that out already. Right. Now what do we do? Okay. Now, so we have this series shunt circuit. What is the first step that we need to do? Okay. Let me mark that here. The first step that we do, step 1 in analyzing this. So we know that this is a voltage circuit, that voltage amplifier circuit that we have here. It's a little bit different to the circuit that you have seen earlier. Okay, but it's pretty much the same, but where we take the output is different, right? So it makes it a voltage amplifier, but otherwise it would have been this is basically a voltage follower circuit, but with a resistor in the collector, right? So that's the only difference. We don't care about that. All we care about is how to do the analysis. Okay, the first step in analyzing any feedback network is step 1. Okay, step 1 is identify the topology, which we already have done. Okay, identify the topology. Okay, how do we identify the topology? We have to ask the question, is the feedback signal or the input signal? Okay, this is XF or either the XF, because they will be in the same type, right? The feedback signal will be the same type as the or the input signal, XS, a voltage or a current. Now in this case, the input signal is given as Vs, so we know it's a voltage, but sometimes this is not clear from the circuit, because say for example, if you have two-stage circuit, the output of the second stage is, so input of the second stage is connected to the output of the first stage, so therefore it might not be very clear whether the input is a voltage or a current, right? But in this case it is clear it's a voltage, but in any case you need to figure out whether the input and the feedback is a voltage or a current. You can do it either looking at the input signal or um, the feedback signal. So in other words, XF applied, whether the XF is applied in series or shunt. Right, so if it is applied in series, it should be a voltage. If it is applied in shunt, it should be a current, right? So in our case, what is my XF? What is my XF? Look, you have to identify it looking at the input circuit. What is the input circuit here? Input circuit is, input loop is this. That's my input loop. Okay, so you have a voltage here. Depending on the, now you can see that current is flowing in this direction, so therefore the voltage is in this direction across this, and voltage across this in this direction. Now this is a AC source, so therefore you can mark this voltage either this way or that. It doesn't really matter. Let me mark it as this. Okay, like that, so that we are consistent with the it doesn't really change anything because it's a sinusoid. It doesn't matter which direction. It's like that. So but to make sure that the notation is consistent, you have that. So what is the VF? This is the VF. Okay, so VF is this. That's my VF. Okay, so therefore I can write XF is the VF across RE. This is across the emitter resistance. So this is in series. So this should be voltage feedback. Now, the second thing is the output. You have to look at the output also to look at the sampling network. Is sampling sampled signal X out, this is the output voltage, output signal, a voltage or a current. That's the second question that we ask. In other words, signal the sampled in series or shunt. Okay. So what is the output? It's clearly given. This is my output also. That's again across the emitter resistor Re. Okay. So it is also the same thing in this case. So therefore, X out happens to be V out across Re. Again, the same. It happened to be the same thing in shunt. Okay, you measure it as a voltage using kind of like a using a voltmeter. So you put it across this. So therefore, this is a voltage series. Therefore, this example, this is a voltage series. So use output is a voltage, you apply it in series as the feedback signal, series or else series shunt. Feedback topology. Okay, we have achieved the first goal. Step 1 is done. Okay, so this is done. Step 2, this is the second step. Draw the basic amplifier circuit without feedback. Now in this circuit we may have feedback, but we are going to draw it without feedback. Okay, draw this basic amplifier without feedback. Now you should what we are trying to do, what in fact we are trying to do is we are going to, instead of analyzing the feedback circuit with feedback, we are going to analyze the simpler case without feedback, and we are going to identify what the value of A is without feedback and the value of beta feedback amount beta in the circuit, and then if you know these two things we can find D, the feedback amount. If you know this, obviously we can then go find the input impedance output impedance without feedback in the simpler circuit. If you know that, and D, we can find any parameter because it's simply either multiplying or dividing each of these quantities by D as appropriate. Okay, so this is what this is what we are going to do. Right, so to do that, first what we do is we have to find out what is the input circuit without feedback. Okay, input circuit without the feedback signal. Okay, so to find the input circuit without feedback, what we are going to do, one, set V out equals to 0 for voltage sampling. In other words, if the output is a voltage, you make sure that voltage is 0. Whatever the resistor that you measure the output across, you short circuit it. Okay, so in other words, you short circuit output node. Okay, so you short circuit this. Now if it is not a voltage. If the output is a current, then set I out equal to 0 for current sampling. In other words, whatever the output quantity that we have, we make that output quantity equal to 0. Right? In this case, if the output quantity is a current, you need to make the current 0. How do you achieve it? By open circuiting the output node. Open circuit, output circuit, output loop. Now what do we have here? We have output is a voltage clearly, right? So what do we do here? Then we need to we have to short circuit this path. It's as if we have a short circuit across there. Okay, so let me mark it in a different color. So you connect a short circuit between this and that. So that will give me my input circuit. So my new input circuit will be will not contain RE. Okay, so that's basically what I'm going to do. So I have the input circuit achieved like this. So set V out equals to 0. The output only has RE in series with the supply voltage Vs, that's between base and emitter. So now what we are going to do is RE removed from the input circuit. So let me just draw the input circuit without feedback. It would look something like this. That would be my input circuit, right? We don't care about the rest of it, right? So we don't care about where the ground is. This is basically the circuit that we see. Now the second thing that we are going to do is to find the output circuit without feedback, to find without feedback. One, if the input signal is a current, it's a voltage, we set it to 0. Set input equal to 0 for shunt comparison. Shunt comparison, if so shunt comparison is not input is a voltage, you use shunt comparison if the input is a current, but in that case you short circuit it, right? That is, it's not the Vs, it's a Vi. Okay, you short circuit the input if the feedback is a current. Okay, so you connect in shunt only for current feedback. Okay, input is short circuited. Okay, so this is if input is a current. Let me say feedback is a current. Feedback signal is a current. Second thing, set input current to 0. That means you open circuit, right? For series comparison. This is input is open circuit. Okay, so this is for if feedback signal is voltage. That's when we compare in series, right? Now for this particular circuit that we have, this is a, oops, I think I have, okay, so in this particular circuit that I have, what I have is a comparison is in series, so therefore it's a voltage signal. So what I need to do is I need to open circuit this circuit, so there will be no current will be 0. What is the current? I, okay, simple I has to be 0. So in order to do that, I need to open circuit this. Once I open circuit that, this IB will not flow through RE. However, I am at this point I am not assuming that IC will also get. Now in actual situation, if I remove IB, IC will also be reduced. IC will also be removed, but I'm not touching IC or IE, right? I'm just removing IB part, because IB in this case, this IE through this is equal to IC plus IB, right? IB is the I input. Okay, so now I'm just going to remove this component, right? IE will then be equal to IC. Okay, so I'm not going to remove that part from this. Okay? So what do I have? Input current II will be equal to 0, which is also equal to IB. Therefore, IC will be equal to IE. Okay, so therefore RC and RE have the same current, meaning that they are in series between collector and emitter. So if I just draw the output circuit would look something like this. The same current will flow through RC and RE, right? I don't care about the input side. Here output is taken across this. This is my V out. That has not changed. Well, V out like that. Okay, that will be my output circuit. All right, so we know that we have this. So therefore, let me draw the. There's the second step, and also the step number 3 is step 3. If your source is a current source, use the Norton's equivalent circuit of the current source. If your if your feedback signal is a voltage, use the Thevenin's equivalent circuit of the source. If your feedback signal is a current, use the Norton's equivalent circuit. Now in this case, it is very obvious. The source is itself a voltage, so it's already in the Thevenin's equivalent circuit form. But as I mentioned earlier, if you had a two-stage amplifier and you are looking at the second stage, you don't know. You have to represent the output of the first stage now either as a Norton's circuit or a Thevenin circuit. Now there you have to identify what is the feedback signal. If you are connecting the circuit's feedback signal to the circuit in series, then it should be a voltage, in which case you draw the first stage as a Thevenin circuit. But if you are connecting the if you are giving the feedback in shunt, that means input to the second stage is a current. So therefore you need to represent the first stage in that case as a Norton's circuit, right? Hope this is clear, right? So therefore that's what we are going to do next. Okay, use Thevenin's source if the feedback signal is a voltage, right? Obviously it can be so this is the source, this is the input. If you know is a voltage, obviously it is already if it is already a voltage source, then nothing to do and you don't have to do anything. But some cases you have to, so in which case you have to figure out what is the type of input which is the same as the feedback type, and then replace it. Okay, and Norton's source if XF is a current. Okay, so obviously what do we have? We already have XF, we know is a voltage, therefore we have to use Thevenin's equivalent circuit. Okay, use Thevenin's equivalent source for the input. Okay, we already have it in this form. Have the source in this form. Okay, so we what is our source? We have the source like that. Okay, so that's my voltage source Vs, right? So now let me combine everything together, right? Those the full circuit then will be, now let me draw the input circuit looks like this, and then I have the source looks like this, and then I have the output. Okay, those are the three components that I have, and this is the output, this is the input, right? So what is my input? This is my input, this is my output, V out. Okay, this is RC, this is RE, RS, VS. Okay, so this is my circuit without feedback. Okay, so this is the circuit without feedback. Remember, I have drawn the small signal model. I have removed the DC source because we don't care about that, right? We are doing a small signal analysis, right? So only the small signal AC equivalent circuit. Okay, without DC. Okay, because our analysis, input impedance, output impedance, gain, we do all these for the AC circuit only. Okay, we are not going to worry about the DC. That is why this is like that, and there is no DC source between collector and the resistor. That is the reason. So this is my circuit. Now it is easy to do the analysis. Now the step 4, step 4, replace each active device with the proper small signal model. Okay, replace each active device, the transistor, with the proper model, because we need to convert this into active linear 2-port kind of a circuit for the transistors rather than 3-port non-linear device. Okay, so let's use the, so for example this proper model can be the H parameter model, or the hybrid pi model, or whatever the appropriate model. Okay, so in this case let's use the reduced version of H parameter model, right? It can be anything. It has to be decided depending on the component values. So use reduced H parameter model. Let's assume this has to be, let's assume HRE is equal to 0, which is very reasonable. Also let's assume HOE also equal to 0. This is not always true. In other words, this is basically the output admittance equal to 0 means this is equal to, say, 1 over HOE is equal to infinity, which means the output impedance, the values of RC and RE are much less than 1 over HOE. That is basically what we mean by this. So HOE, let's say, can be in 100 kilo ohms. RC and RE may be 1 kilo ohms, 100 ohms, things like that. Okay, at least 10 times or more smaller than that. So we assume this is the case. Okay, to make our analysis easy, but it doesn't really matter. We can, even without making this assumption, we can go ahead, but to make things simpler, we'll use that. Okay, so with that, if I draw the circuit again, so we had the transistor, base, collector, emitter, base, collector, emitter, right? So in this arm, let me draw HIE alone. In this arm, let's draw that alone. Okay, so let me mark it as this. Remember, when we this is HIE, this is HFE times II. Okay, so that's my transistor. So in this circuit, I only have to, so that's this part here. The rest of it will be the same. Okay, the rest of it will be the same. So collector and emitter, between collector and emitter, I have two resistors, RC and RE. This is where the output is, right? An input, between emitter and collector, I have emitter and base, we have RS, and the source VS. That's all we have. So this gives me my so this is II, this is V out. Okay, so that's my circuit without feedback, small signal model without feedback. Now if I want to look at the input impedance, where do I look at? I have to look at from here, input impedance, Ri without feedback. R out without feedback has to be looked at from here, R out without feedback. Now if you consider RE to be part of the circuit, then you have to look at it from here. But if RE is considered as a separate outside load, then RE is not there, then you have to look at it from there. So therefore let me call this RO dash. Okay, this is assuming RE contains in the circuit, not an external resistor. If RE is the load itself, in other words, RE is not connected to the circuit. When you take it, you connect an external load resistor. When you connect it only, you have RE. Okay, so if that is the case, we have R out as marked. Obviously this R out includes looking into this node. RC will be in there, but not RE. Okay, RE will be open circuited. Okay, so you are looking at it from this direction. Okay, anyways, we'll mark it like that. Right, so now let's try to find out these things. So step 5, so now we have the circuit here. So the input voltage is this, output voltage is this, right? This is the VI is equal to Vs. Okay, so I think I have marked it the other way around, so let me mark it like this. Okay, initially I marked it like that, so like it like that. It doesn't matter, the direction will be changed. You can actually use it either way, it doesn't really affect the value. Okay, so since current I have marked in this direction, let me mark it as this. If the current I want to mark as this, then I can mark it as this. Okay, remember it has to be consistent. Okay, so if you are changing the directions, you have to change in both. Okay, likewise you can do whatever the direction you want as you wish, they will have to be consistent. So I am marking it like this because I initially marked it in this way. All right, so that's basically it. So the step 5, indicate XF and X out on the circuit obtained by carrying out steps 2, 3 and 4 and evaluate beta equals XF over X out. That's what we need to do. Okay, so we know the X, this is the V out, so this is X out equal to V out. Also, sorry, this direction is this way. No, I think this is right. Direction is this way. And also XF, again XF is also this. So XF is also equal to V out. All right. So therefore, I can write X out is equal to V out. XF is equal to VF, which is also equal to V out. Therefore, beta is equal to VF over V out, which is equal to 1. Okay, so V out divided by V out. So in this particular case, the feedback amount or the feedback factor beta, feedback gain is 1. Okay, so we know the beta value. Step 6, evaluate AV by carrying out or by applying KVL and KCL in the input and output circuits to the equivalent circuit. Obtained after step 4. Okay, so AV is equal to, the voltage gain is V out over V in. V out over V in by definition. Okay, so what is V in? This is my V in, this is my V out. Okay, so what is AV? So since RS is part of the circuit, VI is equal to Vs. Okay, apply Kirchhoff's voltage law to input circuit side, the base emitter circuit, right? So I'm going to apply the Kirchhoff's voltage law in this loop. So this current is equal to this voltage divided by Rs plus He, right? So it's easy to obtain. So from this I obtain I input, which is equal to IB, which is equal to Vs divided by Rs plus Hie. Okay, so here again, this current is equal to this voltage divided by this plus that. Okay, that those are the only elements in that circuit. Okay, so it's easy. I can find II or IB. If I apply the KVL to output circuit, in other words, collector emitter circuit. So this circuit, okay. So this current, the output is equal to, this is the current that is flowing. This current times this plus that will be equal to the voltage as marked. Now I have to change the direction of I because this current is in this way. I have to mark it in this direction, right? So the current in that is flowing like that. So this is my I out like that. So I can write V out is equal to RE times HFE times IB. This is I out, which is equal to RE times HFE times IB is this quantity here, Vs divided by Rs plus Hie. Okay, so therefore I can write the AV is equal to, from this V out, that is this one, over V in, which is Vs. Okay, so this divided by Vs, so that becomes Re HFE divided by Rs plus Hie. So that is my AV, and this is my beta. Okay, so I have these two, so I can now calculate the value of D. Okay, step 7. From A and beta, find D, AV with feedback, RIF, ROF and ROF dash, that is including RE in the circuit and without that. Okay, so this is basically the last step that we need to do. So let me take this to the next page. Okay, so that's step 7. Now we know all this. After that, you know, now the next lecture I will be taking on EE251, so therefore please remain with me. I will complete this and go to that lecture. Okay, so no hurry. Okay, so D we can calculate first. 1 plus beta A, so this actually is common to anything, so let me draw it in. D is 1 plus beta A, so I can find this value. For my specific case, D is equal to 1 plus beta is 1 times A is HFERE over RS plus HIE. So I can bring this as RS plus HIE plus HFERE divided by RS plus HIE. So this is my D. D is like that. So now it is easy to find each of the other quantities. AVF, AV divided by D, which is equal to, what is AV? AV was HFE RE divided by RS plus HIE divided by D. D is this quantity over here, RS plus HIE plus HFERE divided by RS plus HIE. So you can get rid of these. So AVF is equal to HFERE over RS RS plus HIE plus HFERE. Okay, so this is my gain with feedback. Now just to verify some things. Now we know this is a emitter follower circuit, right? It's a emitter follower circuit. So for emitter follower circuit, what should be the gain, voltage gain? Can someone please tell me quickly? Voltage follower, what is the voltage gain? You can't remember? Can someone please tell me? It should be what? It should be equal to 1, right? Remember, for emitter follower means, voltage follower means, it's this voltage is the same in the base and the emitter, right? So therefore gain should be 1. Let's see if that is the case. Now for these circuits, HFE is very high, like 100 or so, and RS and HIE are very small. Okay, source resistance and HIE typically are maybe hundreds of ohms. Emitter resistance typically in the range of kilo ohms. HFE may be about 100. So therefore HFE times RE typically much higher. Okay, so for HFE, which is like 100 or so, RE is like kilo ohms, let's say at least 100 kilo ohms, which is much bigger than RS plus HIE. HIE may be in 100 ohms, RS may be again 1 kilo ohms or something at most. So this is much smaller. So this is a very reasonable value. So therefore, what will be the value of AVF? Will be equal to, so HFE, if I divide everything by HFE, 1 over RS plus HIE divided by HFE RE plus 1. So this quantity right here is almost equal to 0 because of this thing. Okay, so therefore this is roughly equal to 1 as we expect. So this is an emitter follower. Okay, so we know that our analysis is correct in this sense. Again, so the gain is fine. The input impedance, input resistance without feedback, this is without feedback, R in. If you look at the circuit looking into this, right, so therefore that should be this plus that. Okay, these two together, that is RS plus HIE. Okay, RS plus HIE. So that's my input impedance without feedback. So therefore RIF with feedback should be, now how are we going to connect this? In series connection, right? Remember, this is a voltage, so therefore input impedance should increase. So therefore this should be Ri times T, because of series comparison. Okay, so this should be equal to RS plus HIE times D. D is RS plus HIE plus HFE RE divided by RS plus HIE. So I can get rid of this. This will be equal to RS plus HIE plus HFE RE. Right. Again, you can see that RS and HIE are much smaller compared to HFE and RE. HFE RE typically in hundreds of kilo ohms. RS and HIE may be less than 1 kilo ohms or so. So therefore, you can see that the input impedance without feedback, this was in the range of 1 kilo ohm, right? But with this is in the range of, because this is 100, this is maybe 1 kilo ohms, so it should be at least 100 kilo ohms. So that has increased by a factor of about 100. So you see the input impedance properties have improved immensely for a voltage amplifier. So this is why it works as a buffer. Okay, so this is input impedance. Now considering the output impedance, so we know the input impedance, so this RIF is equal to RS plus HIE plus HFE RE. I have already done that. So like that. So now the output impedance. Okay. Now first let's consider, in doing so, RE as an external load. Consider RE as an external load to the circuit. So if there is no load, that means RE has to be infinity, right? RE has to be infinity because we are going to remove RE. So what is the R out? R out, that is with in this case, is equal to the voltage looked into this collector terminal. Okay, looking at from here. So therefore, you have infinite impedance here and RC in series. Now, obviously, if you had this other model where you had the 1 over HOE here, R out would be RC plus 1 over HOE. But now we have assumed this to be infinity. So therefore, this whole thing is also infinity. Okay, that's basically what we have. So this has to be infinity. Oh, 1 over HOE plus RC. Okay. Now, what is the ROF? RO with feedback should be R out divided by D. Now, the thing here is, it looks like it is infinity, right? But this is not the case because D also has RE. Okay, if you look at D also has RE here. So therefore, that has to be infinity also, right? If you are removing it, it has to be removed as from there as well. So therefore, this is infinity, this is infinity. So this is infinity divided by infinity, which is not defined. So how do we go about finding it? Okay, so this is because limit D as RE goes to infinity is equal to infinity, right? That is why. So therefore, it's basically, so what we need is to find, so we don't know what this value is. We need to find it out. Okay. So to do that, first let's find, initially, let's assume RE as a part of the circuit. Consider RE as part of the circuit. Okay. If that is the case, RO dash, output impedance with that in, will be equal to RE parallel RC plus RO. Okay. So in which case, so I'm looking at it here, that will be this in parallel with this plus this. Okay. So therefore, that's basically going to be your output impedance without feedback. But we know R out is infinity according to my assumption. If not, it would be 1 over HOE. If that is finite, then it is again not difficult to figure out. So because this is infinity, we have this equal to RE. So the output impedance without feedback. Now, if that is the case, it is easy to find output impedance with feedback while RE is working as a part of the circuit. This will be then is equal to RO dash. Now, this depends on the equation, whether RO dash times D or divided by D depends on whether the sampling is done in shunt or parallel. Because we have the output as a voltage, we have to do the sampling as shunt, meaning that I have the voltage, the resistance will be reduced. So therefore, I need to divide this by D. Okay, so this will be equal to RE divided by D. Okay, Re divided by D, Rs plus HIE plus Re times HFE divided by Rs plus HIE. Okay, like that. So this is equal to Re times Rs plus HIE divided by Rs plus HIE plus HFERE. So that's my expression for feedback without with feedback like that. Okay, so now I can, if needed, I can find the R out with feedback. That is, if R is part of the external circuit, not part of the amplifier itself, which is, then I have to make sure that limit of ROF this as RE goes to infinity. Okay, so this is equal to, then, so I divide everything by RE, so this will be HS plus HIE divided by Rs plus HIE divided by RE plus HFE. So this will be 0 when RE is infinity. So this whole thing becomes ROF will be equal to HS plus HIE divided by HFE. Now what can you say about this? With feedback, what is HS and HI? These two together will be in the range of kilo ohms, right? So this will be like in the range of, so kilo ohms divided by 100. So this will be, if this was 1 kilo ohm divided by 100, it will be in ohms, like maybe less than 10 ohms or something. Okay, it will be like in the order of 10 ohms or something, very small compared to this value RO value initially was this RO was in the range of, so in the range of RE, right? Oh, this was very big initially. Remember, it was very large. It was infinity in the previous case. The ideal value RO was infinity. From infinity, I have reduced it down to 10 ohms, right? 10 ohms. So this is RO was infinity. So it is now reduced. So what do we like it to be? It's a voltage amplifier. Output has to be very low, right? From a very large output impedance, now I have converted that into an ideal output impedance. So this is the beauty of feedback, negative feedback. Okay, so you don't have to worry about that having a finite large output impedance now, because with this I have converted into a very low output impedance. All right, so this is where we are going to stop this lecture today. Okay, any questions to you guys? Any questions? Okay, no questions. All right, so let me end this presentation here. All right, and stop the recording here.